All right, today we're going to break down one of the biggest reasons even smart programmers get tripped up in coding interviews, a little concept in Python called mutability. So let's jump right in.
And this is the absolute heart of the issue. You can have a brilliant algorithm, your logic can be totally sound, but if you miss this one thing, your code just gives the wrong answer. It's the kind of silent bug that can completely sink an interview, and we're going to make sure that doesn't happen to you. So here's our game plan. First, we'll look at why this bug is so sneaky. Then, we'll get our definition straight before diving into the classic list versus tuple trap. We'll see how it wreaks havoc in real algorithms, solve an actual interview problem, and wrap it all up with a cheat sheet you can take with you.
So, what really makes this bug so dangerous? It's completely silent. You don't get an error, your program doesn't crash, it just quietly messes with your data in the background, giving you wrong answers that are a nightmare to debug when you're on the clock.
It all boils down to one fundamental truth about Python. Variables aren't boxes that hold stuff. They're more like labels that point to objects in memory. Now, if you stick two labels on the same changeable object and you change it using one label, well, the other one sees that change too. This one idea is the root of all these problems, and it all comes down to whether that object is mutable or not.
Okay, so let's get our definition straight. This is the foundation for absolutely everything else we're going to cover.
A mutable object is just one you can change after you've made it. The perfect example is a list. You can add things, remove things, change an element. The actual list object, sitting there in memory, is being directly altered. Lists, dictionaries, and sets are the main ones to remember here.
On the flip side, an immutable object is locked in place the moment it's created. You can't change it. If you try to change a string or an integer, Python doesn't actually alter the original. Instead, it just creates a brand new object and points your variable label to that new one. This is a massive difference.
So why should you care? Because this is not just theory. You get this wrong and your recursive function works on the first test case and then totally bombs on the second. You get this wrong and your dynamic programming solution will literally crash. You get this wrong and that simple loop you wrote will be way too slow and time out. This concept is everywhere in algorithm design. And this leads us to the most classic Python DSA trap of them all, choosing between a list and a tuple. They look so similar, but that one difference in mutability makes them completely different tools.
Here's the simple rule for your interviews. Use a list when you're building something up or taking it apart during your algorithm. Think about tracking your current path and backtracking. Use a tuple when you need to represent a fixed piece of information like a snapshot. Things like coordinates on a grid, or a state you want to use as a key in a DP table. Once for the journey, the others for a fixed point in time.
All right, enough talk. Let's see exactly how this stuff creates actual painful bugs in our code.
Okay, here's the classic scenario. We make a list, A. Then we say B equals A. A lot of people think B is now a new copy of A. It is not. A and B are now just two different names pointing to the very same list in memory. So what do you think happens if we go and modify B?
And there it is. We appended to B, but A changed right along with it. This is that shared reference bug in action. This is what causes so many backtracking problems to fail. A list gets passed down, one function call changes it, and it pollutes the state for everyone else.
So how do we fix it? We have to explicitly tell Python, hey, I want a copy. You can use the .copy method, or my favorite, the slice operator 00. Both of these create a totally new independent list. Now, B is its own thing, and you can mess with it all you want without affecting A. Remember this, it is absolute interview gold.
You know, this isn't just about correctness, it's also about speed. Because strings are immutable, every time you use plus equals inside a loop, you're not just adding a character. What's happening is Python is creating an entirely new string in memory and copying all the old characters over every single time. This turns what looks like a quick operation into a hidden O(n)² disaster. The right way to do it? Append your characters to a mutable list and then join them all together just once at the very end.
Okay, let's take everything we've learned and apply it where it really counts, in complex interview problems with recursion and dynamic programming.
So take a look at this super common backtracking mistake. The same mutable list path gets passed down into every single recursive call. So when one branch of the recursion adds something to the path, that change messes up the state for all the other branches. The list just keeps growing and growing, and all your results end up totally corrupted.
And here's the fix. It's so clean. Instead of passing the same list, we pass path plus I. That plus sign is the magic.
It creates a brand new list for each recursive call. Now, every single branch of our search has its own independent, clean state, and the backtracking logic just works perfectly.
Now let's switch over to dynamic programming. The whole idea of memoization is storing results in a dictionary, right? Well, dictionary keys have to be hashable, and to be hashable, they have to be immutable. This is exactly why tuples are the perfect tool for representing a DP state, like row, column. If you try to use a list, which is mutable, as a dictionary key, Python's just going to throw a type error at you. Let's put this all together with the classic subsets problem. In this buggy code, whenever we find a valid subset, we append the cur list to our results. But remember, we're just appending a reference to that list. So by the time the algorithm finishes, every single spot in our results list is just pointing to the final state of the cur list, which is probably empty. All that work, just gone.
The fix is a tiny 2-character change, res.append cur/. By adding that slice, we're not appending a reference anymore. We're appending a copy of the list at that specific moment in time. We're freezing that state and storing it correctly. In an interview, explaining why you're doing this, because lists are mutable and you need to preserve the state, that shows a way deeper level of understanding.
Okay, we have covered a lot of ground. So let's consolidate everything into a simple little cheat sheet you can use for a quick reference. Here it is. A list is mutable, so it's perfect for things that change, like a path and backtracking. A tuple is immutable, making it your go-to for fixed states and keys in your DP table. And strings and integers are also immutable, which makes them safe to pass around, but just be careful with building up strings in a loop. So I'll leave you with this question. After all this, think about a frustrating bug you had in the past. Does it finally make sense now? I guarantee there's probably one. Mastering this doesn't just help you in the future, it helps you understand your past. If this explainer helped, make sure to follow for more. Next time, we're going to dive into why Python's recursion has a reputation for being slow and why that might not be the whole story.